All right. So yes, hello everyone. This is the lecture number 2 of our course on quantum computing. So today I'm teaching from home. Let me turn off the camera so it makes the video a little bit easy. Right. Okay. So lecture number 2, Introduction to Linear Algebra for Quantum. So this is the topic of our interest for today. And today we're going to discuss the aspects, the basics of vectors, matrices, and linear transformations, with some examples and problems to be solved. All right, so to begin with, let us import the libraries we're gonna use we're gonna use today, which include NumPy, SymPy, and Matplotlib. Another quick aside, let me show you how to get multiple outputs in each session, in each call, right? So for example, if I announce my variable a to be equal something, for example 4, another variable b equal to 2, and then of course I can do multiple calculations with these variables like multiplication, summation, and something more complicated. However, when I run this cell, I'll get only one answer, which is the answer to the very last line here. But usually I want to get the answer to all these requests, right? To do so, I need to import from this interactive shell of Python, basically this line which says that I need to show all the outputs. Okay, I run this cell, and after that, I will be able to see multiple outputs. Okay, so now instead of just the last one, I got all three answers here. Okay, so linear algebra and why it's so important. So linear algebra is a branch of math. We admit other people still come. Okay. Yeah, so linear algebra is a branch of math that deals with vectors, vector spaces, and basically space and vector transformations in the spaces. And this mathematical branch area of math is in the heart of many areas, many applications. The quantum computing is just one example, and of course we have others, and currently maybe even more important. For example, this computer graphics, right? When you save a picture, what your computer does, basically it transforms matrices. Okay, the engineering, electrical engineering, today we analyze these circuits, currents, all this is done through a linear algebra. Economics and finance, another example, and more recent, like more also very actively developing area is machine learning and data science. So all these areas rely on linear algebra. And today, if you would ask me what is the most important part of math, and I would say linear algebra for sure. And if you have some free time and you need to spend this free time for learning, that will be for sure very useful for your future career. Learn linear algebra. So there are a lot of books on this subject. My best one is this book by Gilbert Strang, this former MIT Professor Strang. But there are, of course, a lot of nice books on this topic. So my goal today not to delve to the details, but just give you a crash course on the main things, the things that we will actively use in our quantum computer class. Okay, so we start with the concept of vectors. So you, of course, know what is a vector. Vector is something, it's a mathematical object or geometrical object that gets the length and the direction in some space. Okay, the space itself can be a real space, like space we are living in is a real space, and a vector from real space could be, for example, the velocity of a particle, the acceleration, vector of the gradient of temperature, of pressure, many things. All the things that have the length or magnitude and the direction. And vectors can be also, they can exist in the reciprocal space, which is in a space or like mathematical space, or our auxiliary space, right? So this artificial space that describes some something, right? It can be some sort of a space of some sort of data, etc. The space itself can be of multiple dimensions, potentially even infinite dimensions. And in these spaces, we can define vectors, and these vectors will be of a number of dimensions, right? So why we need vectors in quantum? Vectors in quantum are very important actually because they describe the state of a quantum system. So if you have any quantum system, the system is said to exist in a particular quantum state, which changes in time. And this changing in time of the state of the quantum system is described by a vector and the change of this vector in a particular space. This space is called Hilbert space. And what is a Hilbert space and what makes a space Hilbert space we will discuss in maybe in next lecture. For today, it's enough to say that a Hilbert space is a space of arbitrary dimensions. It can be a dimension of 2, it can be dimension of 10, it can be the infinite dimension. And this space is also a complex valued space, meaning that the vectors in this space are complex valued. Okay, so the vector and every component of a vector gets real value and complex value, or sorry, imaginary value. So we will discuss that in what follows. The way we will denote vectors. So the vectors can be denoted in a different way, right? So like a typical way that you usually see in books, this bolded letter. Another way is to put arrow on the letter, and there is another way which is called Dirac notation, is to place this letter between these symbols, this vertical line and this and this angular bracket. Okay, so this is all three ways we will use in our lecture. So I said that the vectors in the Hilbert space, the space we will work or use for quantum is complex value space. Okay, so the vectors, we need two sorts of the vectors, and for example, in this Dirac notation, we can write them like this, with this angular bracket pointing to the right, and this inversed way when this bracket points to the left. Okay, and these two vectors represent basically the same state, but they are slightly different. We also will discuss this in what follows. Okay, so we're gonna deal with vectors. Vectors represent a state of a quantum system, and since the space in which the vectors exist are complex, we need vectors of two sorts. We call them bra vectors and ket vector. After Dirac, which is famous physicist, right? So he proposed to use this notation. And why bra and ket? Because if you take the inner product of bra and ket, you get bracket, right? So like this word bracket. That's why bra and ket. It's very easy to memory this notation. Okay, so I said that a quantum system is described by a vector in the Hilbert space. And why? And one way to present this is to use so-called block sphere. Okay, so here I put a short piece of code that allow me to show you this block sphere. Okay, so basically in the first line I import this visualization part of Qiskit. Okay, so for now I don't need the entire Qiskit for my project, just visualization part, and I need this plot block sphere function here. Then there is a tutorial, of course, how to use these functions. So this particular function gets the so if the coordinate type says spherical, it means that I use spherical coordinate system. And in this spherical coordinate system, I give the coordinates of the point on this block sphere, and other attributes like fixed size and the title, just decorations. Okay, so if I run this piece of code, I get this block sphere representation. So this block sphere is it represents a two-dimensional Hilbert space. So you might be interested why the three-dimensional sphere represents two-dimensional Hilbert space. The answer is simple. The answer is that this is because the vector shown here by this red arrow is complex valued. So we need the number of dimensions more than 2 to present this state, this vector. Okay, and let's say my quantum system is presented in this state first, and then I study how this system evolves over time. And for example, this angle phi might change over time like this, and this is represented by rotation of this arrow like this. Okay, so the state also can change in amplitude. For example, it can drop in amplitude to 0.5, etc. Right? So this theta angle also can change. So this is a nice way how to represent a state of a quantum system. Block sphere. Okay, so far this was about like motivation, why we need to learn basically vectors and unusual types of spaces, in particular Hilbert space. So now the definition of linear vector space. So linear vector space is a collection of vectors equipped with two operations. Okay, so we have a set of vectors, and we say that this set of vectors define the linear vector space if the vectors can be if you can add vectors to each other, and this addition creates another vector in this space. Okay, like for example, you have one velocity and then you plus another velocity. It generates another the third velocity in the space. And another operation is multiplying the vector by a scalar, some scalar. In general case, it can be a complex valued scalar. And again, multiplication of the vector with a scalar creates another vector in the same space. Okay. Yeah, here are some properties of these operations, including this associativity and distributivity. This is pretty straightforward, right? So as an example, let us consider two vectors v and u, and the scalar alpha. Here I just took simple two simple vectors and this parameter alpha, and I can multiply this parameter alpha by a vector. So this vector is two-dimensional. It gets two components. And how I multiply the parameter with the vector, I just multiply each component of the vector by this parameter, right? So 2 times 5 gives me 10, 4 times 5 gives me 20. So this is the answer. And the same way, using the same algebra, we can take the like a more complex thing, like multiplying the vector by the parameter and then take a plus of another vector here. So when I sum two vectors, I simply sum the components of each corresponding component of the vectors, right? Which gives me this new vector in the same two-dimensional space. The same can be done using Python and in particular NumPy, right? So for example, in this piece of code, I create a vector v. Okay, so this is the way how I create any vector using basically NumPy. If I named NumPy as np, I use this np as a when I call for a function, right, from this library. So NumPy is a library, and it contains many functions. And for now, I need to use this particular one. So I call for a function array from library NumPy. So I write NumPy.array, and then in these rectangular brackets, I simply write the components of the vectors of the vector. Okay, so in this way, it's going to be a horizontal vector with components 3 and 1. In the second line, I create another vector u, which creates the vector with components 2 and 4, and some alpha and parameter alpha. So the same vectors as here. Okay, and if I run this code, it gives me the answer 10, 20, and 17, 9. So basically, in this print, and then so here I multiply my parameter alpha by this vector u and ask Python to basically print the result. I can go, of course, without this print and just write like this. In this way, it will write this array word before the answer. So I want to put okay. Yeah. So in this case, the vectors are horizontal, but yeah, of 2-dimension. And here in this piece of code, this is the example of another 2 vectors with also horizontal orientation or raw vectors, right? And if I write more components here, I can like create a vector of any dimension. I can also specify, for example, that my vector can be complex, right? It can contain complex numbers here. And if I run this code, it will print me the first vector, the second vector, and as an example, the sum of the two. Okay, so now Python understands that these values of the second vector can be complex valued. So for now, it shows me this vector as a real value plus imaginary value with z multiplied by 0. Okay, but potentially we can use also complex value, complex numbers there. I can also write the vector in the column version or vertical vector like this. So there is a rule how to write the components. Okay, so when I write the components, I create this np.array, then parentheses, and then the let me start. Let me write this from scratch. So I call this function here, okay, and then I say that I need to write a matrix because any vector is actually a matrix. And then I fill up this array with components, component by component. So, and row by row. Okay, so I write the second rectangular brackets here. And for example, I need a matrix like 3 by 3 with some components like this. So this is my first row. Then I put column, the second row, so this, and then another row. Okay, and it's gonna be in this case it's gonna be a matrix 3 by 3 with these components. And if I run this, it will show me this nicely looking matrix. Yeah, so this brings us to the point of matrices. Matrix is a generalization of a vector, right? And in Python, this matrix can contain as many rows or columns as needed, right? In this way, it is essentially a table of some numbers, maybe data. I can multiply these vectors created over here, right? Vector one call. So vector 1 is this one, vector call is this one. So I can multiply them with a number, some parameter. So here is a vector 1. Here is the vector 2. So in this way, yeah, I can separate the lines. For example, printing an empty line here. Okay, so it's the answer 1, answer 2. Okay, so this brings us to the concept of linear independence. So very important point. So a set of vectors and the sets of vectors we show in this figure brackets, right? So a set of vector is linearly independent if no vector in this set can be expressed as a linear combination of other vectors in the set. Okay, so this basically means that this set of vectors is unique. You cannot represent, for example, v1 through linear combination of other vectors. Linear combination means these vectors multiply by any parameters. And for example, here, like for the vectors v1, v2, they are linearly independent if this expression, some alpha, which is parameter, can be complex parameter, times v1 plus beta times v2, never equal to 0 for any non-zero alpha and beta. Okay, so if alpha and beta is 0, then 0 is 0. This is trivial. But if you require this alpha and beta not 0, then the vectors are called linearly independent if this expression is always non-zero for any alpha and beta. The geometrical meaning of this is very simple, right? So linearly independent vectors are simply orthogonal vectors. So for example, in this coordinate system x and y, the x is horizontal, y is vertical, right? We can, for example, introduce these unitary vectors I and j. These unitary vectors with the length 1, okay? And these vectors are orthogonal. You cannot transform I to turn it to j. So you cannot express I in terms of j and vice versa. Important point here to understand is that this, for the particular space, there is an infinite number of such vectors, such sets of vectors. For example, if coming back to this two-dimensional xy space, right, I can consider this I and j as the set of linearly independent vectors, but I can also rotate the space or rotate the vectors and consider the other two, like v1 and v2. And these vectors also are orthogonal, and they also are linearly independent. Okay. So for example, let us consider two vectors, v1 and v2, with these components. v1 is with components 1 and 2, and second vector with components 2 and 4. So I took this example because it's very easy to say the answer from the very beginning, right? Because v2, this vector 2, is just a simple multiplication of the vector 1 by the constant 2, parameter 2. But anyways, so how we define whether the vectors are linearly independent? So we basically write this characteristic equation. We take some alpha times v1 plus beta times v2, and ask whether this system can be equal to 0 for any non-vanishing, non-zero alpha and beta. Okay, so plugging in these values for the vectors v1 and v2, I get this system of equations over here, right? And after simple algebra, I mean, these algebraic expressions, we can get this answer that alpha is equal to -2 beta. So basically, for any beta, like you can say 1, right? You can find any non-zero alpha, which means that these two vectors are linearly dependent. Linearly dependent. What it means, the vectors are linearly dependent. It means that you cannot use them as a basis to describe all other vectors in the space. Okay, and vice versa. If the vectors are linearly independent, you can use this set of vectors to represent any other vector in the space. Again, the set of these linearly independent vectors is not unique. You can simply rotate the space and get another set. But the number of these vectors is always the same for a particular space. Okay. Yeah, so by the way, how we can check the linear independency using, for example, NumPy. Okay, so I return to this system of equations here, and I notice that I have this matrix, right? Characteristic matrix 1, 2, 2, 4 multiplied by a vector alpha and beta. Okay, so I write this matrix of coefficients 1, 2, 2, 4. And then there are several ways how to check the linear independency of the vectors. For now, we can simply check if the determinant of this matrix is 0 or not. Okay, so if the determinant is 0, then the matrix is singular, and that means that the vectors are linearly dependent. So I have this matrix here, and then I write a simple code, which is, by the way, a nice example of the syntaxes of Python, right? So I can use this operator if. So I literally say that if the determinant, so this is the function I use to calculate determinant of any matrix. We will return to this point a little bit later today. So I just call this function, okay, and check whether this determinant equal to 0. Okay, so this is the Boolean operation which checks if the determinant is 0 or not, and it returns two options, true and false, right? So if the return is true, then the code is asked to print this line here. The matrix is singular and the vectors are linearly dependent. And there is another line here in this construction, this else, right? So if this is wrong, this is false, then this line doesn't work, right? And the program jumps to this line else. So if else, so if this determinant not equal to 0, then the program is asked to print the matrix is linearly independent. Okay, so I can run and check this. So it returns me, for this particular one, it returns me the line that it is linearly dependent. I can change this matrix, for example, put here free here, right? And in this case, the matrix is linearly independent. Again, which means that I cannot transform one vector to another vector. For the space, for two vectors is rather trivial, and but this function, this operation can be upgraded to the space of any dimensions. Yeah, speaking about dimensions, so I said several times this word dimension. What is dimension? And dimension of a space is literally a number of linearly independent vectors. Okay, so for example, in this case, we have two linearly independent vectors. So this space is called two-dimensional space because we have only two linearly independent or orthogonal vectors, which are I and j, or v1, v2, right? So the number of linearly independent vectors defines the dimension of the space. Okay. And in this case, this number of linearly independent vectors is called a basis. The basis because we use the basis to represent any other vector in the given space. Okay, so for example, I can write. You of course know all these formulas. This is rather like elementary math, right? So let's say I am in a space of n dimensions, okay? And I introduced a basis of linearly independent vectors, and usually we normalize them to the length 1, so they are unitary normalized. The vectors e1, e2, all the way up to e1. So these are the unit basis vectors. So then I can represent any other vector in this space just taking this expression, right? The summation over the multiplications of the projection of the vector on the direction of the basis vector by, multiplication of this projection by the vector itself. Okay, so for example, if I express this this formula here, I will get something like this, like the projection on the axis on the vector 1 times e1 plus projection on the vector 2 times e2 plus etc. up to vn times en. And again, this n can be infinite, actually, for infinitely for the space of infinite dimension. Okay, so if we normalize the lengths of these basis vectors to 1, we can also represent these vectors in the space through their vectoral representation, right? For example, this E1 generate or represented by this vector column with components 1 and all the other zeros. And then the second vector is 0, 1, and then all zeros, etc. And finally this En vector is given by this column, all zeros except for the very last element, which is 1. So the vector. So using this vector form for the basis vectors allows us to to represent any vector v in this space through its projections on the basis vectors. Okay, so any vector will be uniquely presented through the projections of the vector on the basis vectors. But this works only after I set the basis vectors, right? Because, as I said, even though the linearly independent basis vectors are unique, you still can transform them one basis to another basis. And there is an infinite number of bases in any space with dimension more than one. However, after you set this basis of vectors, you can represent any vector in the space through its components or projections of the vector on the basis vectors, like this. At this point, also I noticed this. It's called Einstein summation rule. Okay, so it's basically easier way to write the these expressions like this, like the product of vectors in this form. So you basically omit this summation sign in any expression where the summation index, you meet this index twice. So for example, if I consider this expression here, I have this VI, EI. So this I is the summation index, and I can omit this summation sign over here and just write VI, EI. So this is just the same thing. So having the space and basis introduced in the space, I can do something with the vectors in the space, right? And one thing I can do, of course, as we already discussed, I can multiply the vector by constant, which means changing the vector magnitude, vector length. I can subtract and add vectors one to another one, and this creates another vector in this space. And of course, I can take the product of vector, with another vector. And there are three types of product. And the first one is inner product. In books, it's also called dot product or scalar product. Scalar product gives the, because the result of this product is actually a scalar. So let's consider two vectors, A and B, and I can form this inner product. And by the way, this inner product sometimes in some books is written like A dot B, sometimes like this parenthesis A comma B, and sometimes just A times B. Essentially, it's just the same thing, right? And the answer is component of the, so this is the summation of the products of the components of the first vector and the second vector. So if I would write this in expanded form, it would be A1 times B1 plus A2 times B2, etc. Okay. The way we get this formula, so basically I have this inner product here, right? A times B. So I substitute for the A, its representation in the projection form, or component form. And for the vector A and for the vector B, I substitute them to this expression. So here is the result. And then I regroup the terms. Here I simply write AI, BI, then this product of the basis vectors, EI, EJ. So these are the same vectors, right? This EI and EJ are the same vectors in this given space. And if I consider the product of this EI and EJ, I will see that I can actually write them, the product of these two, the product of these two vectors over here, right? So for example, if I take the product of E1 and E2, it will give me 0 because the multiplication by components give me all zeros. So the answer will be 0. However, if I take vector E1 and multiply by itself, I will get 1 in this first position. So it will give me it will be 1. So all these can be summarized in this Kronecker delta. So this matrix here is known as Kronecker delta. So this is basically a matrix of zeros, or all zeros except for ones on the main diagonal here. So main diagonal is 1, and all other indices are zeros. Okay. And this Kronecker delta helps me to simplify the things. For example, if I have an expression like this, the summation of the components of vector B times this delta Kronecker Ij, right? So I have this summation index j here and here. For any given I, the Kronecker delta will be 0 except for j equal I, right? Which means that I can simplify the summation and simply write the answer like bi. So I simply replace the index j by index I here. That's what I'm doing. The same way we can write. So I already write this over here. So this is just simple repetition of the product of two vectors A and B. Okay, so I can write this product as a summation of the products of the components of the vectors A and B. The same holds for just one vector. I can take the inner product of vector by itself, and it gives me the square of the vector, right? And if I take the square root of this value, it will return me the magnitude of the vector, or modulus, absolute value of the vector. Absolute value of the vector, which is essentially the magnitude or length of the vector in the space. So this is the first example. This is rather trivial in terms of Python, so I probably decided to not provide any examples here. But yeah, so we can of course, let me see. Yeah, we can write something here to as an example, right? So for example, if I create a new cell and then I create one vector, let's say A, to be consistent with what's above, then what's numpy array then something like, I don't know, something like simple 1, 2, another vector B with components say 3, 4, right? And I can print the sum of two, or so we're discussing the product, so the product of the two. So to do so, I do A times B. It's gonna return me the the answer, right? So it's simple product of the components of the two vectors. Why it returns me the array? Let me see. So it returns me array because actually I need to transpose the second vector. So we will talk about transpose a little bit below. Anyways, so this is the way how we take the, we take the dot product in Python. I just need to come to the point of transpose so we can write this in a correct way. This is actually a very good point to notice that when you take a product of two vectors, it's not sufficient just to multiply vector by vector, right? You actually need to multiply one vector by the transpose version of the second vector in order to get this scalar here. Anyways, so the dot product, that product is very important for quantum. And as we will see, this dot product will allow us to calculate the probabilities in any quantum experiment or quantum calculation. So the dot product is important. Cross product is, less important. So let's go through this just very quick. So suppose I have two vectors, and in contrast to dot product or inner product, which creates a scalar in return, the cross product generates another vector. And let's say I have two vectors A and B. The cross product creates the vector which is orthogonal to these two, to the vectors A and B. Okay. This is the way how it's written. Usually A cross B, or this rectangular brackets A comma B. And essentially, this is the determinant of such a matrix, right? With the basis vectors in the space we are in currently, and components of the vector A and vector B. So here is the way how we find the determinant. I leave it for you because we will return to this point, to the point of determinant a little bit later. This is just for you how to calculate determinant if needed. And finally, the final type of product we will need is so-called tensor product. Another way to call this is dyadic product, but there is a difference between tensor and dyadic. So in contrast to inner product, which creates scalar, and cross product, which creates a vector, tensor product creates a tensor from two vectors. Okay, so this is like a generalization of the two. And this is the way we denote tensor product, with this circle with cross inside. Sometimes you call this O cross or something like this, or tensor product. And essentially, what you do is very simple. So you have this first vector, then you take tensor product and second vector, A and times B. And what you do, you simply multiply each component of the first vector by entire second vector. Like here, I take this first component of the first vector and multiply by this entire vector B here. And the same for the second component. And in return, I get the vector with 4 components. Okay, so I started from two-dimensional vectors, and the result of tensor product is 4-dimensional vector. Where we will use it. So as we discussed actually in the first lecture, I noted that we need a system of many coupled qubits, right? And so essentially, every time you add a qubit to your system, what you do this tensor product. Like, for example, if you have a system of 2, and first qubit is represented by vector A, the second qubit is represented by vector B, their system of the 2 interacting is described by the tensor product of the 2 vectors. Okay, so a system of 2 qubits will be represented by a vector with 4 components. And if I add another qubit to the system, I will multiply this again by 2. So it's going to be 8 component vector. Not only vectors, but also matrices and tensors need this generalization, right? Because because if I have a matrix that acts on a vector, and then I generalize this vector to the space of 4 dimensions, then I also need to generalize the matrix also to the space 4. Okay, and this is basically the way how we do. So this is basically the same thing. So you have one matrix, you tensor product the second matrix, and you simply multiply each element of the first matrix by entire matrix B. So here, to make it like tidy, I put this definition for the matrix like this. And this is basically probably the first time we encountered this this hat on top of the letter. So when I write this hat on top of a letter, I specifically denote this is a matrix or operator. Okay, sometimes I use this hat on top of the letter, sometimes don't. This is just like for convenience. So by the way, do you still see my screen? Because I don't see this green frame around.
Yeah, I still see your screen.
Awesome. Yeah, thank you. Yes, and this is probably a good time to ask you for any questions. Do you have any? There's no questions in the chat. So if not, then let me yeah, so there is a very useful notation for this tensor product, also like widely used in quantum computing. So this tensor power, right? Like, for example, a vector, some vector A to the tensor power of n is simply the number of tensor products of a vector by itself. Like, for example, a vector to the tensor power of 1 is simply the same vector, but a vector to the tensor power 2 is just a tensor product of vector by itself, which generates this vector of dimension 4. And the same for tensors and for vectors. For example, a matrix like this to the tensor power of 2 generates this matrix of 4. Yeah, so let us consider a quick example. An example is about three-dimensional Euclidean space, which is simply our three-dimensional space we live in, right? So, for example, we have this three-dimensional space, and we can introduce the axes. Schematically, we present them by axis x, y, and z, right? And if you look at the corner of your room, this can be like one wall, this can be another wall, this can be a floor, right? And you can easily imagine this axis x, y, and z in your room. In this space, we introduce the basis vectors I, j, and k. These are three linearly independent vectors, and there is only three vectors which are linearly independent. All other vectors will be defined by these three. Okay, including this arbitrary vector v, which, for example, shows or indicates the position of, whatever, or my position in the room. And this vector, given like this, can be given by or represented by the projections of this vector on the axis x, y, and z. Right, so this is pretty straightforward. Just as a reminder. Yeah, so the projections themselves can be found through the cosines of the corresponding direction angles, like the angle between vector v and x is angle alpha. The angle between v and y is angle beta, and the angle between v and z is angle gamma here. So this is how we calculate these projections. And as we discussed, this magnitude of the vector is given by the square root of this square, the summation of squares of the components of the vector, which can be for two vectors v and b in this space can be written in this form, right? Simply the summation of the products of the components of the vectors vx bx plus vy by plus vz bz. Pretty straightforward. And finally, the tensor product of these three-dimensional vectors. Three-dimensional vectors also can be written like this. Yeah, and finally about dyadic product, which also useful. So dyadic product is simply a tensor product, but this second vector here is taken transpose. Okay, so instead of vector column, you transpose it and get vector row, this horizontal vector. And when you multiply this vertical vector with horizontal vector, you get, I mean, another way to represent the things. So you get, instead of this vector of how many, 3, 5, 6, 7, 8, 9, 10, 10 components, you get, I guess, 9 components, you get the matrix of 3 by 3 written like this. So this is another way like to create a tensor. So in this case, it will, the product or the result will be a tensor. But this is just terminology, and you, of course, supposed to very well know all this. So now we come to matrices and matrix operations. Do you have any questions about what we've discussed so far? I'm trying to go like detailed and step by step, because there are some things here that I need you to understand very well, even though you, of course, know or supposed to know all these things. Still, there are some key points that are rather important. One important point here is the need for tensor product. Okay, so this is generalization of or representation of multiple multi-qubit systems. We will discuss this. Oops. Yeah, okay. Another point is these basis vectors. So for a space of dimension n, we need n basis vectors to represent any vector in the space. However, the number of sets of basis vectors is infinite, because I can take any particular basis and simply rotate it by any angle. And since there is an infinite number of angles, I can rotate it. The infinite number of basis sets exist. This is important because what actually quantum computing is doing, or what quantum computer does, is it takes a space, a Hilbert space, and rotate it. Okay, so we will discuss, but essentially the quantum computing is a combination of so-called quantum operations. Okay, we call them quantum gates, and each gate takes the vector or takes the basis, the computational basis, and rotates it by a certain angle. This is how it works. So this is important to understand these things. And if you have no questions as yet, let me transit to matrices. So matrix, I mean, of course, you're familiar with matrices. You, of course, know that we can sum the matrices. We can multiply the matrices by constants, by the summation of constants. There are also these properties which are rather straightforward. Let me actually transit to two types of multiplications of the matrices. And to do so, I create two matrices, one A and another one B. And to keep the things like a little bit more general, I take these two matrices of different shape, right? So the matrix A gets 2 rows, 3 columns, and the matrix B gets 2 columns, 3 rows. And having the matrices like this, I can multiply them. The first way to multiply matrices is so-called Hadamard multiplication, or you're probably more familiar with this element-wise multiplication. So this is basically just multiplication of each corresponding element of each matrix. And to do so, of course, this, I mean, in order to get this Hadamard multiplication possible, you need these matrices to be of the same to the same shape, right? That's why, for example, in this case, so for example, if I have matrix A and I want to multiply by itself, I can simply write A star A. This is Hadamard multiplication by default, and it gives me another matrix, which is basically A squared. However, if I have another matrix of different form, different shape, for example, my matrix A, as I said, is 3 by 2, no, 2 by 3, but B matrix is 3 by 2, so the shape is different. But I can transpose this matrix B. So instead of 3 by 2, it will be 2 by 3. So it will be the same shape as the matrix A. And in this case, I can multiply element-wise, multiply the matrices. Without this transpose, it will give me the error. So it says that operands could not be broadcast together with different shapes. So this is one important thing here. So the next type of multiplication, more important one, is matrix multiplication. So what is a matrix multiplication? Matrix multiplication, there is a rule for matrix multiplication. Okay, so if you, for example, have two matrices like this two, the result is a matrix. Okay, and the way you get each element in the resulting matrix is you take a row in the first matrix and column in the second matrix, and take the product of the components and sum up all the products. For example, in this case, it's going to be 1 times 7 plus 2 times 9 plus 3 times 11. You sum up all the things and you get 58. And the number of elements, the position in this matrix, is defined by the number of the row and the number of the column in these matrices. For example, this element is going to be 1 row, 1 column, right? The second element here will be multiplication of the row of the first one by the column of the second one, and so on. The way how we calculate this using math, using Python, is this one. Let me remove the print for now. So say I have these two matrices, A and B, right? I can ask Python to basically take the slice of the first matrix. I'm doing this way. So the slice, as we discussed in the first lecture, right? You do the slice with the, I mean, this is the syntaxes for that, taking the slice of the row, like the first, this matrix A, and then you take the slice of the first row of this matrix. Again, the number of the rows and columns and the element of in any list, array, matrix in Python starts from 0, okay, and ends by n-1. So 0 means 1. So the first row of the first matrix times the first column of the second matrix. And then I sum up all these products, and I get the result, which is 58. So this is exactly what we expected to get, 58. And the same way, you can take these slices and products of them, some summations for all the 4 elements of the new matrix, and print the result for this matrix multiplication. As you can see, it's very difficult way to do so, right? Of course, there is a operator for matrix product. It's simple add. Here, you simply write A add B. It gives you the same result. Very easy, very straightforward. So thus far, we used NumPy, which is numerical library for the Python simulations. Sometimes we prefer to use SymPy, which is symbolic Python library, which allows us to work with mathematical objects, like in the way we used to, like writing formulas in symbolic way, right? So, for example, how we use this SymPy for matrices. So first, you always need to announce a number of mathematical objects, like variables, letters, right? In this case, A, B, C, and etc. You call this function symbols from library SymPy, and you give them like a way how to represent these symbols. For example, if I run this and typing B, you create a new cell. And for example, if I want to see how this variable A presented, this is how it works. However, of course, I can change this and write something like, I don't know, whatever. I can use LaTeX syntaxes here to write basically anything. And so now, oops, why it doesn't work? No, supposed to be. Let me see. Yeah, so I don't need this dollar signs when I use symbols. That's depends from library to library. Some of the functions, of course, for example, for the matrices, right? For example, this transpose. In NumPy, in SymPy, you can do the same thing, like transpose the matrix. But the syntax is a little bit different. So you always, so when I use Python, I always Google. Like some people joke that like 90% of the time of coding is Googling basically. And of course, you can put whatever, and it will be changed. So you can give any name, any symbol to represent any of these variables, like this. And given the symbols set A, B, C, D, E, F, G, H, I can I can create these 2 matrices, A and B. So now I type SymPy matrix with capital M, and then create this matrix the same way as in NumPy. So the syntax here is the same. And then I ask to print A and B, and now you see how like now this matrix is like nicely represented in a way we used to when you write formulas and in articles, papers. But now this A, B, C, D, etc. They are not just letters. They actually mathematical objects. I can give value to each of this particular letter and work with them like with a mathematical object. For example, I can take the sum of the two, and it creates this summation of two matrices. You can check the product of the two matrices A and B. This is the result. And here I put this note that this is important to notice the difference between SymPy and NumPy. So if you go back to NumPy, we notice that this star denotes the Hadamard elements element-wise product when element times element, right? In SymPy, this star denotes the matrix product. So you can see this here. So this is the last line calculated is this one. This is the result. And this is exactly the matrix product, which we discussed over here, right? This is the matrix product. And the same way, if I run this line, this last line, this add symbol, it gives me the same result. So in SymPy, the star and this add gives the same result, which is the matrix product. This is important to to keep in mind when you transit between NumPy and SymPy. So a few words about commutation of matrices and commutator. In algebra, when we deal with simple numbers, integer or floating, whatever, the result doesn't depend on the order of multiplication. Like 2 times 3 is equal to 6, regardless of the order. 3 times 2 also gives you 6. So it doesn't matter. For matrices, it actually does. So if you write two matrices, and for example, you take A times B, so the result will be, highly likely it will be different. It usually different than the result B times A. So when you exchange the order of multiplication of two matrices, the result changes. And in order to check whether the matrices commute or not, so the fact that they commute means that the order doesn't matter. If they don't commute, we can introduce this commutator presented like this, which is simply the difference between the two options, right? A times B minus B times A. So I can calculate something like this for two matrices I just introduced. And here is the result. So we see that in general, two matrices are not commuting. However, this is for commutator, right? So this is already the difference. However, if these elements would be equal to 0, then two matrices will commute. Then the commutator will be 0. And this means that I need to, if the matrices satisfy these 4 requirements, there are actually 2 requirements here. So, but I mean, in general, yeah. So if the matrices satisfy these requirements, the matrices will commute. Otherwise, they don't. So here I introduce more symbols like this. which allows me to create other two matrices, C and A, in order to show how we numerate the elements in matrices, right? So the first index stays for row, the second is for column. So this is first column, this is the second column. First row, second row. And numeration, of course, starts from the top left corner and goes down and right. This is also important. So having this matrix C, for example, I can calculate the determinant. You remember that for this simple matrix 2 by 2, in order to get determinant, I take the product of the diagonal components, C11 times C22, and subtract the product of the off-diagonal components, C21, C12, right? And of course, we can do this using SymPy. So in SymPy, it's pretty simple. I just write, I call this, it's called method, right? The method, the name of the matrix dot determinant with parentheses, and it returns me the determinant of this matrix. And of course, if the matrix is is more complex, higher dimension, this defining of determinant is could be a complex task, but Python does this in one single line of code. Transpose. So transposition of a matrix is simply rotation of the matrix over the main diagonal, right? So for example, if I also return this matrix C here, matrix C here, right? So it C11, C212, C21, C22. The transpose version of the matrix is the rotation over the main diagonal. So these two elements, the off-diagonal elements, exchange. And there are two ways to find transpose. You can simply type .t capital or .transpose. This is just a way of, I mean, you like. In NumPy, of course, we have also transposition, transpose, and in this line, for example, so I cannot use these matrices for NumPy because NumPy is for numerical, right? I cannot use letters here. I need to use numbers, particular given numbers. And in order to create some matrix, I write this line of code, which here creates a matrix 2 by 2 with random values. Then I round these numbers, okay, to not keep all these numbers after the decimal point. For example, if I remove this function, the result will be like this. This is also fine, I guess. So let me print empty lines so I can distinguish them. Okay. And then, yeah, so this printing this, the matrix itself gives me this matrix. And then I print the transposed version of the same matrix. And yes, indeed, this is the same matrix, but rotated across the main diagonal. There is an important property for transposition of matrices. We state that if you transpose the product of two matrices, you have to write them in the reverse order, like the product of C and A transpose is equal to A transpose times C transpose. And if we have like more matrices here, B, C, A transpose, then we have to write the transpose, the product of transpose matrices in the reversed order. This is also quite important. We can check this out. For example, I write the product in SymPy, I write the product of two matrices, C and A, and take the transpose, and I take the difference of this with what's on the right side, right? And if this is true, I'm supposed to get 0. Yeah, this is the 0 matrix. However, if you forgot about this important property and write in the same order, C and A, here the result will be something like this, which is completely wrong. So like this. All right. So transpose. The next one is inverse matrix. Inverse matrix is a matrix that being multiplied by the matrix itself. So for example, I have some matrix C. I take the inverse matrix C, indicated this inverse operation indicated by C to the power of -1, right? So this is indication of inverse matrix. So if I multiply this inverse matrix by itself, it returns the identity matrix in reply, which the identity matrix is all ones on the diagonal and zeros off diagonal, right? So this is the definition of inverse matrix. How we calculate inverse matrix? So at this point, I used to spend some time writing formulas and calculating these inverse matrices by hand. Now I think that this is maybe not very useful for the quantum computing itself. This knowing how exactly to do so. You can watch on our YouTube channel and our lectures from the last semester, for example. I just want to show how easy it is to get this inverse operation in Python. So I just run this methods dot inf, standing for inverse, and it returns me the answer. Okay, so in all these four components of the matrix get the determinant of the initial matrix in the determinants, and the components of another matrix composed of the minors of the matrix itself. So this is very easy, and of course, for 2 dimensions, it's also rather straightforward. We have formulas for this, but if you go to dimension of 5 or 10, etc., this operation is very handy, very useful. Yeah, for inversion, NumPy has this function np.linealg.inversion over here. Again, no need to memorize all these things, these functions. It gets to you with practice. Of course, Googling helps all the time. Yeah, so for now, this NumPy, we cannot use the letters. We have to use actual numbers. And if I generate this matrix of random numbers 2 by 2, it returns me this operator inversion, returns me the inversion matrix of the given one. Some important properties of inversion matrices. One is very similar to the what we just discussed for transpose. So if you take the inversion of the product of two matrices, you have to write the matrices in the reverse order. The inverse matrices multiplied in the reversed order. And another funny property is that transpose and inversion, you can exchange them, right? So the inverse of transpose is equal to transpose of inverse. Pretty simple. So why we need inverse matrices? The arithmetic reasoning is that inverse matrices help us to find or to solve the systems of linear equations, right? For example, here I wrote some arbitrary linear equations, three equations, three unknowns. So most likely I can solve this. One can solve this analytically, of course, but for the system of three, it takes some time. But you can rewrite this equation, these linear equations in the matrix form, and notice that this matrix of coefficients, right? This matrix coefficients multiply by this vector of unknowns x, y, and z. And if I introduce the names, right, for these matrices, for example, my matrix of elements is A. Here, the unknowns is X. Here, and this left coefficients on the right is B. I can rewrite these equations in this simple form. Matrix A times vector of unknowns equals to vector B. Okay, and of course, if this would be just numbers, I would divide both parts by this A, right? And this give me the solution for X, which would be B over A divided by A. However, since this A, B, and X, they are vectors and matrices, I cannot divide. We cannot divide by matrices. So we need to use this definition for the inverse matrix and multiply this expression here by inverse matrix A from the left both sides. So when I multiply this part by A inverse, and here B by A inverse, this A inverse A on the left side cancel down, right? It generates this unitary identity matrix, and identity matrix times X returns X. So this is the solution for the system of linear equations of any order. It can be 3, as in this case. It can be 5, 10, it can be thousands, it can be millions. All these solutions is these things. The only computational problem here is to find this inverse matrix. Okay. So for example, I guess this is for example. This is example for this particular case: 1, 3, minus 7, 6, 2, 15, minus 2. Yeah. So this is the matrix A. This is the vector B, and I ask Python to find the inverse of this matrix A, right? So this is A inverse. And then I take the tensor matrix product of this inverse A with vector B. So basically here write this line. And it returns me this vector C. And I just run this cell, and it returns me this vector of unknowns. So this is the solution to this system of linear equations. Pretty simple. A few words about, we have some minutes left. A few words about complex conjugate matrices. Again, in order to take the complex conjugate, you just call for this method dot conjugate parentheses. So basically, if you have a complex number like this, J, I remind you, is a imaginary unit, the way we define imaginary unit in Python. And I need to take the conjugate, complex conjugate of this number. I just run this, and it returns me the same complex number, but the sign, right? So it was plus, now it's minus. So it complex conjugation changes the sign at or by the imaginary part of complex number. The same works for matrices. For example, here I generate a matrix 2 by 2 with complex numbers. Okay, so all these numbers are complex. So this is the matrix generated. And then I call this function conjugate, this method conjugate, and this is the result. So again, it just changes the sign of every imaginary part in every complex entry in the matrix. It changes the sign of imaginary part. There are two ways to call this function conjugate, either this way as a method or as a function, numpy.conjugate, and then you put the name of the matrix in this between parentheses. The last thing for today, Hermitian conjugation. So Hermitian conjugation is a combination of two, transpose and complex conjugation. Okay, so if you have a complex valued matrix with complex indices, elements, in order to get Hermitian conjugation, you transpose it, which means rotation over the main diagonal, and complex conjugate every element in the matrix. All right, here is the example. I generate a matrix of complex values, and then ask Python to get Hermitian conjugation. Here is the syntaxes. So the name of the matrix dot and the name of this method for Hermitian conjugation, get H. The same can be done in SymPy, for example, for this matrix here, with these elements defined. I can do Hermitian conjugation with this simple .h. Yeah, basically the way how it's done in SymPy, .h. And here I check what's the difference, right, between this matrix C and the Hermitian conjugated matrix C. Here is the difference. For quantum mechanics and for quantum computing, of particular interest is Hermitian matrices. So the particular interests are Hermitian matrices. So Hermitian matrix is a matrix that stays unchanged after or upon Hermitian conjugation. Okay, so transpose and complex conjugation doesn't change the matrix. This is interesting. And in order to get, in order for matrix C to be a Hermitian, we can see that these elements, all elements must be zero, right? So we see that. So this line over the element indicates the Hermitian conjugation. So from here we see that these diagonal elements must be real valued, and these off-diagonal elements must be conjugated for a matrix to be Hermitian. So what is this example? An example of Hermitian matrix. Yeah, so here is an example of Hermitian matrix. Okay, so we have these real values on the main diagonal and complex values on the off diagonal, but they are complex conjugated. So the difference in sign here and here. So when you transpose this matrix, these two off diagonal elements exchange, but then you take the complex conjugation and the sign returns to plus again. So the matrix stay unchanged after Hermitian conjugation. And let's check that. So for this matrix C, I take this minus CH, and it returns me 0 as expected. Very last thing, very simple thing, linear transformations. So in any linear space, matrices act or can act actually as an operator that change a vector in the space. So I have a space with a vector. If I act some kind of matrix on this vector, this operation changes the orientation of the vector in the space. Okay, so for example, for the vector state 1, 0 in the two-dimensional space, I can create some sort of matrix. It's probably is the same matrix as above, like this one, or maybe this 4 here. So I put 4. And I also create the inverse matrix for, we will see for what. So this is the matrix, just some arbitrary matrix. In this case, it is a Hermitian matrix, but it doesn't really matter anything. And so for the given state, I can multiply the state with the matrix, and it will give me another vector like this. Okay, so we started from this vector here, 1, 0, and then this matrix acts on the initial state and creates this new vector, which belongs to the same vector space. A point here to understand is that for this given matrix, I can create the inverse version of this matrix, right? And if I act this inversion matrix on this final state, it will return me the initial state. So this way I can basically change a vector, right? So this is linear transformations. How it works, the basis of linear transformations. We will talk about this more in what follows, because as I said, all the quantum computation is essentially the operations of linear transformation. So you have quantum system with a given quantum state, and then you apply these quantum gates, which transform the vector, this quantum state, in the Hilbert space. So this is end for today. Thank you very much. Let me stop the recording and then we can discuss.